Hi guys, so we're going to be doing the cure optimization of Thermosetting Adhesives Lab. So like we've done in all of the other labs, we're going to break down each of those words because it's a lot of words that you probably don't understand. So cure, right? What exactly is a cure in industry? So a cure is basically a process in which adhesives or polymers go through that creates a much harder or like a much stronger bond, right? So that's what we're going to be dealing with today. We're going to be dealing with a cure. There are some things in life that we use that can be cured, more specifically super glue, wood glue, a bunch of other things that have to do with adhesives, right? So I don't know if you guys have seen Gorilla Glue, Gorilla Wood Glue. Whenever you get popsicle sticks, you have to wet it before you place the adhesive on top of it. Now when you wet it, that's kind of like the curing agent. That's what it needs in order to create a stronger bond. So if you guys have seen that before, you have your popsicle stick and you wet it beforehand, you place the adhesive and then you clamp it down, and what you're going to end up seeing is you're going to see the adhesive itself expand and then completely contract. So when it expands, that means that the molecules are elongating, and when they contract, they're coming together to form a much stronger bond, right? So in the curing process, in this lab specifically, we're gonna be dealing with time and we're gonna be dealing with temperature. You guys are going to stick to a specific temperature, whether it be 120, 125, 135, or 140. But for this specific lab, we're gonna keep it at one temperature. It's 135, correct? Yes. Okay. So we're gonna keep it at 135, and we're gonna have time being our changing factor, right? So that's based on curing, right? So cure optimization. So what exactly is optimization? We're gonna be finding the best, and what exactly is the best? We'll get to that in a little bit. Thermosetting adhesives, right? So I know that y'all probably haven't talked about polymers in your lecture, but polymers can be broken down into two different categories. So there's thermosets and thermoplastics. So we'll talk about thermoplastics beforehand. Thermoplastics can be reshapen, recycled, and they can be broken down into two different categories: amorphous and semi-crystalline polymers, right? Semi-crystalline polymers are a little bit more opaque because they actually have crystals embedded into it, whereas amorphous thermoplastics don't have crystals. So now we can talk about thermosets, which are what are going to be in the lab, right? So some examples of thermosets can be like what you find on your keychain. They can be rubber tires, because if you think about it, thermosets, they do not melt. They are very, very hard to reshape, and they don't melt. They end up degrading, right? So if you think about it, you wouldn't want to have tires that melt in the valley heat. So these are what we're going to be using. We're going to be using thermosets, right? And so based on those two adhesives, we're going to have an old adhesive and we're going to have a new adhesive. The old adhesive is going to be a beige color, and the new adhesive is going to be a red color. And so that's what we're going to be doing today. So right here, if you guys see, we're going to be having 1 through 4. These 4 specimens are going to be part of the old specimens, or the old adhesive, and these 4 are going to be the new specimen. Now, what exactly are we going to be doing with these? So we're going to end up taking our adhesives, putting them into these coupons right here, and we're going to put them into the oven. And when we put them into the oven, we're going to take 1 old and 1 new specimen out at the 30-minute mark, and then we're going to keep the timer going. At the 45-minute mark, we're going to take another old, another new, and then at the 60-minute mark, another old, another new, and then at the 75-minute mark, another old and another new, right? And so with all of this going on, we're going to find out which one or which time is the best one when we put it into the MTS machine, and we're going to pull them apart. So if y'all think about it, based on what we've done in the past labs, we've dealt with tensile strengths, right? But in this case, we're going to be dealing with shear, right? So shear is basically the sliding force that is going to be occurring at the MTS machine, right? So whichever one of these holds the largest load is going to be the best option for optimizing, okay? So not only that, what you guys want to remember as well is in industry, time is money. So the longer that a process is, the more expensive it's going to be as well. So if you think about it, let's talk about the new specimens, right? The new adhesive. If we had a 30-minute, the 30-minute specimen holds, say, 100 pounds of force, right? But we had the 75-minute hold 110 pounds of force, right? I mean, obviously, you would think, okay, maybe the 75-minute one would be the best one, but in reality, I think that it's okay that we can sacrifice a couple of extra pounds of force for a shorter process that holds almost the good amount, but will save us time and save us money in the end of things, right? So I'm going to show you guys how to set those up. So in here we have our freezer, and there's already a couple already cut out, so I'm going to go ahead and use those. But just for the purposes of the lab, I'm just going to show you guys how to do this because you're going to have to put it in your procedures. So I'm just going to get this right here. So this is the Old adhesive. This Old adhesive, with your hands on it and the heat from your body, it's already going to start to do this, right? And so I know that you can't really feel it, but it ends up getting to the consistency of a fruit roll-up. So the area that you're going to have to be cutting is 0.5 inches squared. So you're going to go 1 by a ½ inch. So you're going to take this right here, 1 full inch. That's already cut there, luckily. There. And when we throw this back inside, once we throw that back inside, we're able to just let it harden up like that. Remember when it started doing that and started getting to the fruit roll-up type of phase, that just means that it was already starting to cure. Okay, so we come right here. That's the ½ inch, perfect. Like that. All right, so this is what we ended up cutting off, all of our specimens. So this is going to be our setup right here. So what you're going to end up doing is you're going to place this right on top of it. Make sure that it connects right there. And remember, this is pretty sticky. It's already starting to cure. So we're going to get this right here. Oh, there's this one right here. We want to make sure that all the sides are clean, that there's no previous adhesive on it. We're just going to place these directly on top of it. And then we're going to place this clamp right here. And we don't want them to be crooked like this. And the reason for that is because when we put into the MTS, it'll give us weird results if we do so. But there we go. So that's going to be our specimen. And so we just have to do that for each of them. All right, guys, so we have our oven set to 135. We're going to place all of our specimens in. It doesn't matter where. We just have to be quick with it. Here, and we're going to grab this one over here and do the exact same thing. Close that up. So we're going to wait till it gets to 135 again, and then we're going to press go on our timer or our stopwatch. Okay. All right, so we're going to be using the MTS, just like using the tensile tester from before. We were dealing with tensile forces. This time we're going to be dealing with shear force, right? So the only difference between this and the tensile testing process is that this has flat plates right here so that it could fit our very thin specimens, right? So we're going to go ahead and start off with the 45-minute old. We could have started off with the 30-minute specimens, but something ended up happening with it. So we're going to start off with the 45, and this is what you're going to do for every single pair that you guys have. So for the 30, 45, 60, and the 75. So we're going to go ahead and place it in here. I'm going to place that there and tighten it up here. And then once again, we're going to drop this down like that, and we're going to tighten it up. Okay, so here we go. That's our first specimen. So now we're going to come over here and we're going to go to monitor. So from right here, what you can see is we have our width and our thickness as the 1 inch by a ½ inch. That's going to give us our area of 0.5 inches squared. And now we have our initial speed of 2 inches per minute. And so since we already have this all done, we don't need to change anything. So what we do have to do is zero out our signal here on the load, and we're going to zero out our signal here at the crosshead. All right, so now we are going to press play and we're going to see what happens. So nothing too crazy happened, but you did hear that very big snap. So we're gonna take out the specimens. That fell in, okay. And we'll get that one right now. Then you're gonna come over here, you're gonna return it to 0. And then from here, you're going to get your peak load right there. So remember, this is for 45 minutes of the old specimen. And so we got up to 783 pounds of force. So that's the only thing that you're gonna end up taking down for both specimens. Now, what you're gonna have to do for your notebook is you're gonna have to get the shear stress. So one way to do that is just to use force over area. So you're gonna divide your peak loads by the area of our adhesive, so the 0.5 inches squared. All right, so now we're gonna do our 45-minute new specimen. So we're gonna do the exact same thing, but as you can see, these are a little bit longer, and if we were to use that, it's probably not gonna catch it all the way, so we're gonna go ahead and pick up the crosshead a little bit more. Like right there is good. Okay, so we're gonna go ahead and place this inside. Hit it downward, tighten it up, and hit it upward and tighten it. All right, so there's our specimen. So now we're gonna come over here and we're gonna do the exact same thing. So we come over to monitor, everything is exactly the way it is. We have to zero out our signal on the load and zero out our signal on the crosshead. And then now we press play and okay. All right, so now you guys can see that this specimen held a lot more of a load than the older adhesive, right? So the one thing that you're gonna have to figure out, so we're gonna do return to 0, yes. And once again, you're going to get down the peak load. This one held much more of a load than the old adhesive, right? Now, the one thing that we didn't talk about in the other video that you guys are going to have to make a remark of is what types of failures that can occur in this lab. So there are 3 failures that can occur. One is the adhesive failure, the other one is the cohesive failure, and the last one is an adherent failure, right? So this one right here is an adhesive failure because, as you can see, the bond between the actual adhesive and the coupon itself completely failed, right? So as engineers, we do not want this. We do not want the bond between those 2 mediums to fail. Now this one right here, the cohesive failure, this one's a little bit different. The cohesive failure has the adhesive on both sides, but the biggest thing to remember is that it is the adhesive itself that failed. This is what we want because this will actually give us what the properties are of the material itself, right? And the last one, adherent failure, that's basically where the coupon itself shatters, and we're not going to see anything cool like that in this lab. So other than that, you're going to end up doing the exact same thing. You're going to get the peak load right there, and you're going to end up dividing that by the area in order to get your shear stress. And so after that, what you're going to end up doing is you're going to be making graphs, right? So one graph that you're going to end up making is the shear stress by the time, right? So when you're doing this, you're going to end up doing one graph for the old and one graph for the new, or you can put them together on the same graph. It doesn't really matter, whatever you guys prefer, but you guys have to have this graph nonetheless. So shear stress on one end, or on the y-axis, and time on the other, on the x-axis, right? And so from here, that's where you're going to end up finding out what time is the best one out of the entire temperature that you guys are testing at, which is 135 degrees.